Welcome everyone. Today we're diving into linear programming relaxation. Think about packing a suitcase. You really need whole items. But sometimes it helps to first imagine slicing them into fractions to see how everything fits perfectly. In the same way, we'll relax those tough integer constraints into a smooth, continuous form so we can solve problems lightning fast with linear programming. Along the way, you'll learn how to extract useful bounds and steer yourself toward high-quality, approximate solutions. Ready to see how this transformation can make your life and your optimization so much easier? Let's dive in. With that foundation, let's turn to integer programming. An integer programming problem asks us to minimize or maximize a linear objective function, but with the important twist that both the decision variables and the constraints binding them must take integer values. When our goal is to minimize, it's called a minimization integer program. If we aim to maximize, it's a maximization integer program. The key takeaway? Integer programming is nitrogen monophosphide hard, so as the problem grows, finding exact solutions quickly becomes extremely challenging. Next, we'll explore how relaxing these integer constraints to allow continuous variables leads to a linear programming relaxation that can guide us to high-quality, approximate solutions. Now let's look at a simple binary integer program. Our goal is to maximize the sum of two decision variables, x plus x. We're bound by three linear constraints. 4xx cannot exceed 8, 2x plus x must be at most 10, and 5x2x has to be at least minus 2. Finally, both x and x can only be 0 or 1. This tiny example shows how adding integer restrictions turns an otherwise straightforward linear program into a concise combinatorial puzzle. Building on our earlier binary programming example, this slide illustrates the concept of a feasible solution space in constrained optimization. On the horizontal and vertical axes, we plot our decision variables, x and x. The blue polygon shows all points that satisfy the constraint inequalities, the feasible region, while each green line represents one inequality of the form A is less than or equal to B. Notice that this region is non-convex. The inward dent along the top edge creates more than one locally best point. The red label local optimum marks a solution that's optimal in its immediate neighborhood, but not the overall best. To find the true optimum, we introduce the objective's direction vector c, drawn as a red line and arrow. Imagine sliding this line in the direction of increasing objective value. The very first contact with the feasible region occurs at the red dot labeled x. That point is the global optimum. No other feasible point yields a higher objective value in direction circa. Key takeaway: non-convex feasible sets can trap you in inferior local optima. By aligning your search with the objective's direction, you ensure you uncover the true best solution, x. Here, we survey the main algorithms for solving linear programs. First up is the classic simplex algorithm. Despite its exponential worst-case complexity, it almost always finds solutions very quickly in practice. The real breakthrough came with the ellipsoid algorithm, the first to guarantee polynomial time performance, though in practice it tends to run more slowly. That, in turn, spurred the development of interior point methods, another family of polynomial time algorithms whose efficiency on large-scale problems can rival or even surpass simplex. Taken together, these results firmly place linear programming in the class P. It can indeed be solved in polynomial time. To put these ideas into practice, let's examine a straightforward linear programming model. Our objective is to maximize the function x plus x subject to three linear constraints. 1. 4x minus x is less than or equal to 8. 2. 2x plus x is less than or equal to 10. 3. 5x minus 2x is greater than or equal to minus 2. Das. We also require x is greater than or equal to 0, and x is greater than or equal to 0. Together, these inequalities carve out the feasible region, and our task is to find the point within that region that yields the highest value of x plus x. Now that we've defined our linear programming model, let's explore a few popular solvers. First, there's a convenient web-based interface you can try immediately at zwagmedia.com/realworld/simplex.html. If you'd like to embed LP routines into your own code, the GNU Linear Programming Toolkit, GLPK, offers a C-based library of callable functions. LP-Solve provides similar functionality, with libraries available for both C and R. For more advanced needs, CBC, the CoinOR branch, and CutSolver comes as a C++ library or a standalone executable. And finally, MATLAB includes built-in functions for defining and solving LP models directly within its environment. Now that we've explored LP solvers, let's see how linear programming relaxation can help us tackle nitrogen monophosphide hard problems. First, we express the original challenge as an integer program. Then we relax its integrality requirements, replacing each integer constraint with a linear one to form a standard linear program. Because LPs can be solved in polynomial time, we quickly obtain a fractional solution. Finally, we leverage that solution to reconstruct a valid integer answer for the original problem, often yielding a surprisingly good approximation. Now, building on that framework, let's walk through the standard LP relaxation workflow. First, we take our original integer programming model and simply drop the integrality constraints to form a classic linear program. Next, an LP solver quickly produces an optimal fractional solution. Then comes the crucial rounding stage, where we convert those fractional values into a valid integer solution. Finally, that integral output serves as our approximate answer, or can even be fed into further algorithms for refinement. Because the quality of our approximation hinges on how well we round, this step is usually the most critical. Now that we've outlined the LP relaxation workflow, let's turn to a concrete example, the vertex cover problem. Given any undirected graph, we want to choose as few vertices as possible so that every edge touches at least one selected vertex. In other words, we're looking for the minimum size subset of vertices that covers all edges. In the example on screen, the orange nodes form a valid vertex cover. Every red edge is incident on at least one highlighted vertex. Finding that smallest possible set is exactly the challenge at the heart of the vertex cover problem. Building on the unweighted case, let's now introduce the weighted vertex cover problem. Here, each vertex in our undirected graph carries a numerical weight, and we still need to cover every edge by choosing at least one of its endpoints. The twist? We want the sum of the weights of our selected vertices to be as small as possible. Take a look at the diagram. There are 7 vertices labeled with weights 5, 5, 10, 4, 2, 1, and 9, all connected by red edges. A valid weighted vertex cover must include at least one endpoint of each red edge, and the real challenge is finding the combination of these numbered vertices whose total weight is minimal. Building on what we've just seen, here is the integer programming formulation of the weighted vertex cover problem. We introduce a binary decision variable x of v for each vertex v, set to 1 if v is included in the cover and 0 otherwise. Our objective, shown in equation 35.12, is to minimize the total weight, VWV x of v. The critical constraint in equation 35.13 ensures every edge, u, v, is covered by requiring x of u plus x of v is greater than or equal to 1, so at least one of its endpoints lies in the cover. Finally, equation 35.14 enforces the integrality condition x of v element of 0, 1. Together, these 3 components capture exactly the minimum weight vertex cover as an integer program. Now we relax the integrality requirement on each xv, allowing it to take any value between 0 and 1, yielding the familiar linear programming relaxation. Our new objective is still to minimize the total cost. Minimize underscore element of v, w of v, quex x of v, but the constraints become purely linear. Nide. For every edge u, v, enforce x of u plus x of v is greater than or equal to 1 to ensure each edge is covered. 2. For each vertex v, impose the upper bound x of v is less than or equal to 1. 3. Finally, require non-negativity. X of v is greater than or equal to 0 for all versus with the integer constraint replaced by these linear bounds, we obtain a program solvable in polynomial time. Even better, its optimal value provides a strong lower bound for the original integer problem, and it often inspires the approximation algorithms we'll explore next. Building on that relaxation, we see that by turning our 0 to 1 integer program into a linear program, we automatically secure a valid lower bound on the integer optimum. Since every binary vector lives in the continuous box, 0, 1, any feasible integer solution remains feasible in the LP. Consequently, the best value you can achieve in the linear program can't exceed the best integer solution. It always sits at or below the true optimal value of the integer program. Building on our LP relaxation insight, we now present a simple two-approximation algorithm for the minimum weight vertex cover problem. First, we solve the LP relaxation to obtain an optimal fractional solution xy. Next, we round each variable by including every vertex v for which xyv is greater than or equal to 1/2. Those vertices form our cover C, and we then return C. By choosing the 1/2 threshold, we guarantee that the total weight of C is at most twice the weight of an optimal cover. This straightforward rounding scheme, often called the round half up method, runs in time dominated by the linear program and achieves a factor 2 approximation. Now that we've outlined our rounding approach, let's confirm it always yields a valid vertex cover. The procedure is simple. 1. Begin with an empty cover set C. 2. Solve the LP relaxation of the minimum weight vertex cover problem to get an optimal fractional solution, x1, 3. For each vertex v, look at x1. If it's at least 1/2, add v to C4. After processing every vertex, return C as your cover. Why does this work? In the LP, every edge uv satisfies xy's is greater than or equal to 1, so at least one endpoint must have xy's is greater than or equal to 1/2, and thus belongs to C. In other words, every edge is covered, guaranteeing that C is always a feasible vertex cover. Now, to show that C really is a valid vertex cover, pick any edge, u, quanta, v. The LP constraint tells us that xu plus x of v is greater than or equal to 1, so at least one of those values must be, is greater than or equal to 1/2. Our rounding rule then adds every vertex with x is greater than or equal to 1/2 into C, which means u or v or both ends up in C. Since this argument applies to every edge, C indeed covers all edges. Building on that proof, let's outline the 3 key criteria any approximation algorithm must satisfy. First, feasibility. It always yields a valid solution that meets every problem constraint. Second, tractability. It runs efficiently because the underlying linear program can be solved in polynomial time. And third, quality. We can prove the solution's value stays within a known bound of the true optimum, ensuring it never strays too far from the best possible answer. Building on our discussion of the quality guarantee, let C be an optimal solution to the minimum weight vertex cover problem, and let z denos be the optimal value of its linear programming relaxation. Since any integer cover is a feasible LP solution, z denos serves as a lower bound on the weight of C. In fact, we can express nos at theta z denos equals vwv doppelmaker sub v, which immediately gives z denos is less than or equal to w of C asterisk. Finally, let C denote the cover produced by our approximation algorithm. By the optimality of C denom, we know W of C asterisk is less than or equal to W of C, so chaining these inequalities yields Z dnaps is less than or equal to W of C asterisk is less than or equal to W of C. This chain shows that our approximation's cost never falls below the LP bound and never exceeds the true optimum by more than the ratio implied by our rounding. Building on that chain of inequalities, let's now express the weight W of C of our chosen cover in 2 equivalent ways. First, W of C is simply the sum of the weights W of V over every vertex V in our integer solution C. Second, since our rounding rule picks exactly those vertices whose fractional value x of V is at least 1/2, we can equally write this sum over all V and V with x of V is greater than or equal to 1/2. In other words, the cost of our rounded solution matches exactly the total weight of vertices whose LP value reaches the 1/2 threshold, showing how our integer cover aligns directly with the fractional solution's values. Building on our previous observation, let's express the cost C of our chosen vertex set C as the sum of its vertices' weights. Door Corway C equals underscore V element of C WV. This E got. By construction, C contains exactly those vertices whose LP value x1V is at least 1/2. Hence, we can rewrite that sum as C equals underscore versus x1V is greater than or equal to 1/2 W of V. Next, notice that whenever x while V is greater than or equal to 1/2, the factor 2 dic while is at least 1. Therefore, W of V is less than or equal to 2 dic while V, can mean x while. And summing over the same index set gives C is less than or equal to underscore versus x while V is greater than or equal to 1/2 W of V while V. In other words, the total weight of our integer solution is bounded by twice the LP objective on those vertices, yielding our factor 2 guarantee. Continuing from our last bound, we express the cost of our cover C as the sum of weights of its vertices. C equals underscore V element of C, WV. By construction, every V in C satisfies x while V is greater than or equal to 1/2. So for each such V we have WV is less than or equal to 2 WV new V x own of. Substituting this into our sum gives the first inequality. C equals underscore V element of C, WV is less than or equal to underscore V element of C, 2 WV V. Next, notice that extending the index set from C to all of V can only increase the sum, yielding C is less than or equal to underscore V element of V, 2 WV all of V equals 2 underscore element of V, WV all of V. Finally, since underscore V element of V, WV x score V, is exactly the optimal LP value Z, do, we conclude C is less than or equal to 2Z, completing our proof of the factor 2 approximation. Building on that bound, let C denote the total weight of the vertices we've picked. By definition, C is just the sum of W of V over every chosen versus, since we only include vertices whose relaxed value x 1/2, each term W of V can be bounded by 2 jumblib W of V. Any C's we can't x1. Summing over all vertices gives C is less than or equal to 2 dwext V W of V xyv equals 2Z. Remember, the optimal LP value Z times is a lower bound on the true optimum C times, and we also know C is greater than or equal to C times. Putting this together, CC is less than or equal to CZ is less than or equal to 2. In other words, our algorithm never does worse than twice the optimal cost. So it's a clean 2 approximation. Now, let's take a step back and walk through the LP relaxation workflow. We begin with our integer programming formulation, then relax its integrality constraints to turn it into a linear program. That LP is passed to an LP solver, which returns an optimal fractional solution. The most critical stage is the rounding step, where we convert that fractional result into a feasible integral solution. Finally, that integral solution can be evaluated, or even fed back into the original integer program for further refinement. With that in mind, let's shift our focus to a classic problem in this space, MaxSat. Here we're given a Boolean formula in conjunctive normal form and asked to choose truth values that satisfy as many clauses as possible. A simple baseline, nicknamed the one-down-mulum, just assigns each variable to true or false with equal probability. It's super easy to implement and guarantees that, in expectation, we satisfy at least half of all clauses, so it's a 0.5 approximation. Today, though, we'll look at a stronger approach, the John algorithm, which bumps that guarantee up to about 0.637. To see it in action, consider this formula: .x or not x, and of x or not x, and not x or not x or x. Even here, pure random assignment hits 2 out of 3 clauses on average. But with the ASOUN algorithm, we push that fraction significantly higher. Building on our improved 1-2 algorithm, let's now see how to cast MaxSat as an integer program. We begin by encoding each Boolean variable with a binary decision variable x, where x equals 1 if the variable is true and 0 otherwise. Next, for every clause C, we introduce another binary variable y, setting y equals 1 exactly when that clause is satisfied, and 0 if it isn't. As a concrete example, consider our running formula, x or not x, and x or not x, and not x or not x or x. With x and y defined this way, we're ready to write an integer program whose objective is simply to maximize the total number of satisfied clauses, i.e., maximize the sum of all y variables. Now we convert our maxset setup into a 0 to 1 integer program. We introduce a binary variable 11 for each Boolean variable and a binary variable yj for each clause. Our objective is simply to maximize the total number of satisfied clauses, i.e., maximize n array summation yj. For every clause j, we enforce the constraint n array summation xi over all positive literals in clause j, plus n array summation 1 xi over all negated literals in clause j, is greater than or equal to yj. This way, yj can only take the value 1 if at least one literal in clause j is true. Finally, we declare all xi and yj to be binary, 0 or 1. As a concrete example, consider our three-clause formula, y, x1 or not x2, and x2 or x3 or not x4, and not x1 or not x3 or x4. Beta. Each of these clauses gives rise to 1. Sum of literals is greater than or equal to yj constraint. Solving the resulting integer program then yields an assignment that maximizes the number of clauses we can satisfy. Building on our integer programming formulation for maxsat, we now show how to relax it into a standard linear program that we can solve in polynomial time. We introduce two sets of variables, x, representing the truth value of each Boolean variable, and y, indicating whether clause j is satisfied. Our objective is to maximize the sum of all y's. To enforce clause satisfaction, we require for each clause j that chorus, sum of x over its positive literals, plus sum of 1x over its negated literals, is greater than or equal to y. This ensures y can only reach 1 if at least one literal in clause j is true. Finally, we constrain every x and y to lie between 0 and 1. If we insisted that x and y be integers, this formulation would exactly capture maxsat, but it would be hard to solve. Instead, we drop the integrality constraints and solve the relaxed linear program in polynomial time to obtain an optimal fractional solution, x times y nops. The key insight is that the sum of the fractional y-time values gives an upper bound on the maximum number of clauses any Boolean assignment can satisfy. This bound becomes the cornerstone of our approximation analysis. Now, building on that LP relaxation, we start with our integer programming model and relax its integrality constraints to turn it into a standard linear program. We then hand this relaxed problem off to an LP solver, which returns an optimal fractional solution. Next comes the rounding stage, where we convert that fractional solution back into a feasible integral solution. Finally, we map this integer solution back to the original problem. This LP relaxation plus rounding cycle lets us leverage fast, linear programming techniques to infer high-quality integer solutions. Building on our LP relaxation and rounding framework, randomized rounding boils down to just two simple steps. First, we solve the linear programming relaxation to obtain an optimal fractional solution, x asterisk, x asterisk, x asterisk. Then, for each I from 1 to n, we independently set x to true with probability x asterisk, and to false otherwise. Remarkably, this procedure always produces a feasible integral solution in polynomial time. What's left now is to understand just how close its objective value comes to that fractional optimum. Building on our randomized rounding scheme, we now bound the probability that a single constraint C underscore J is satisfied. We start with B100 of bat. PRC underscore J is satisfied. is greater than or equal to 1 underscore j, caret underscore j, caret asterisk underscore j. Noting that 1 underscore j, caret underscore j is less than or equal to 1, E allows us to substitute and obtain. PR underscore j is satisfied, is greater than or equal to 1 slash E caret y asterisk underscore j. Next, by applying linearity of expectation across all M constraints, the expected total number of satisfied constraints is equals 1 slash E fex y underscore 1 plus y asterisk underscore M. Since the optimal integral value, C dime can be no larger than y time underscore 1 plus y asterisk underscore M, we conclude EC slash C is greater than or equal to 1 slash E, which gives us our 1 slash E approximation guarantee. Building on our overall approximation guarantee, we now zoom in on a single clause C and establish a firm lower bound on the chance it's satisfied by our randomized rounding. Concretely, we want to show PR is satisfied, is greater than or equal to 1 caret asterisk. To get there, let's examine the complement, the probability that C fails. Since each literal in C is rounded independently, we can write PRC is unsatisfied equals underscore I element of positives 1 dash X asterisk underscore I element of negatives X asterisk. Next, we invoke the fact that the product of non-negative numbers is at most their arithmetic mean raised to the number of factors. In other words, if you sum all those failure probabilities, 1x asterisk for positive literals and x asterisk for negative ones, divide by C, and then raise that average to the th power, you get PRC is unsatisfied is less than or equal to underscore I element of positives 1x asterisk plus underscore I element of negatives x asterisk 1xe each allowed 1x asterisk 1x asterisk. Finally, our LP constraint guarantees this average failure probability is at most 1 C whenever y asterisk equals 1. Plugging that in and flipping the bound gives exactly PR is C is satisfied, is greater than or equal to 1 caret y asterisk, which completes the single clause analysis. Building on our previous bound, we now quantify the exact probability that a particular clause C underscore j remains unsatisfied under the random rounding. First, we write the failure probability as the product of two parts. The chance every positive literal fails, underscore I element of C, underscore j caret plus, 1x underscore I, times the chance every negative literal flips to true, underscore I element of C, underscore j caret, dash x, underscore I. To simplify this product, we invoke the arithmetic geometric mean inequality, shown at the top. Concretely, we replace the entire product by its arithmetic mean raised to the C underscore j power. After regrouping terms, this yields the compact upper bound, 1 dashed underscore I element of C underscore j caret, plus x underscore I duntov plus underscore I element of C underscore j caret, 1x underscore I, C underscore j caret underscore j. This form makes it crystal clear that, once we account for the average satisfaction weight of the literals, the failure probability decays exponentially in the clause size. With this bound in hand, our next step is to plug in the LP constraint and flip the bound to obtain the familiar exponential lower bound on the clause satisfaction probability. Building on our previous bound, let's now encode MAXSAT as an integer linear program. We introduce a variable x underscore I, element of 0, one for each original Boolean variable, and a variable y underscore j, element of 0, one for each clause. Our objective is to maximize the sum of all y underscore j's that directly corresponds to the total number of satisfied clauses. The heart of this formulation is the highlighted constraint. For each clause j, sum of x underscore I over its positive literals, plus sum of 1x underscore I over its negated literals, is greater than or equal to y underscore j. In plain terms, y underscore j can only reach 1 when the clause is truly satisfied by the x's. Solving this LP in polynomial time then yields an optimal fractional assignment whose total y value upper bounds the maximum number of satisfiable clauses. Now that we've solved the LP and obtained our fractional solution x times and y times, let's analyze the chance that a particular clause Cj ends up unsatisfied under randomized rounding. Since each positive literal I is rounded to true with probability cam signs, and each negated literal with probability 1-vine vems, the exact failure probability is own. PRCJ unsatisfied equals n airy product I element of Cj plus 1xi asterisk. Fitty n airy product I element of Cj element of Cj element of Cj xi n. To simplify this product, we invoke the arithmetic geometric mean inequality. By grouping all Cj factors together, we get the upper bound. N airy summation I element of Cj plus 1x summation plus n airy summation I element of Cj summation I by factory Cj. Next, recall the LP constraint that ties these x values to yj asterisk. N airy summation I element of Cj plus xi times plus n airy summation I element of Cj ajj dash red dash it 1xi asterisk is greater than or equal to yj asterisk. Substituting into our bound and rearranging gives the elegant result. PRCJ unsatisfied is less than or equal to 1yj asterisk. Cj. This concise bound is critical. When we sum it over all clauses, it immediately yields the classic 1-to-1/e approximation factor for max SAT under randomized rounding. In the next slide, we'll see how these per-clause bounds combine to complete our approximation analysis. Building on our previous bound, let's now look at the probability that a particular constraint C is satisfied under our randomized selection. Notice that C can only fail if none of its elements are chosen. So we get PR satisfied is greater than or equal to 1y asterisk caret. Next, we invoke a classic inequality. Replace y asterisk with 1c in the base and raise the result to the power y asterisk. That gives us PRC satisfied is greater than or equal to 1-to-1 caret asterisk. In other words, each constraint is guaranteed to be satisfied with at least this constant probability. Building on our previous bound, let's introduce the function .f of r equals 1-1-k caret k. For r in 0, 1, and any positive integer k, our goal is to show that f of r never dips below a fixed fraction of r, namely f1r. Since f1 equals 1-1-to-1 division slash k caret k, the inequality we're after is simply .f of r is greater than or equal to f of 1 half r. Take a look at the graph on the right. The red curve is fr, climbing smoothly from 0, 0 up to 1 f1, while the black straight line is the chord connecting those same 2 points. Because fr is concave, the red curve always stays above its chord. That geometric fact is exactly why fr is greater than or equal to f1r for every r in 0, 1. This neat intuitive bound will drive our simulation argument forward without getting bogged down in dense algebra. Building on our earlier definition, we now introduce f of r equals 1-1r division slash k, and claim that for any r in 0, 1, and any positive integer k, f of r is greater than or equal to 1-to-1 division slash k / r. On the left, you see the statement and a brief proof. We start by checking the trivial cases k equals 1 and k equals 2 by direct computation. Then, assuming k greater than 2, observe f0 equals 0 and F1 equals 1, 1-to-1 division, slash k. Fr equals 1r division, slash k, is greater than or equal to 0, so f is non-decreasing on 0, 1. Fr equals k1k, quicker as 1r division, slash k, squared is less than or equal to 0, so f is concave. By concavity, the red curve Fr must lie above the straight line joining 0, 0 to 1, F1, and that line is exactly y equals F1r. This elegant chord argument gives us the desired inequality in one simple step. On the right, the graph illustrates this beautifully. The red arc of f of r arches above the black diagonal line y equals F1r, making the proof's core insight immediately clear. Building on that chord-bound insight, we now derive a tight lower bound on the probability that a given constraint C is satisfied by our randomized rounding. First, observe that the chance of covering C is 1 minus the probability that none of its candidates is selected. Plugging in the total fractional weight y asterisk spread evenly over these items gives us PRC is satisfied is greater than or equal to 1 minus y asterisk C caret C. Next, since y asterisk is less than or equal to 1, we can simplify the base to 1 minus 1c and raise it to the exponent, y asterisk yielding PRC is satisfied is greater than or equal to 1 minus 1 caret y asterisk. Finally, recalling that 1 minus lambda slash r caret r approaches e caret minus lambda, as r grows, we set lambda equals 1 to arrive at the clean exponential bound. PRC is satisfied is greater than or equal to 1 minus e caret minus y asterisk, and then use the fact that 1 minus e caret minus t is greater than or equal to 1 minus 1 slash e caret for t in 0, 1. Altogether, this gives PRC is satisfied is greater than or equal to 1 minus 1 e caret y asterisk. In other words, every constraint is satisfied with at least a 1 minus 1 e fraction of its fractional LP weight, exactly what we need for our overall 1 minus 1 e approximation guarantee. Building on that exponential bound, we now show how it yields our overall approximation guarantee. First, for any clause j, the probability it's satisfied is at least 1-to-1 slash e y asterisk underscore j. Summing over all m clauses gives e seq 1 to 1 slash e quad underscore j equals 1 caret my asterisk underscore j. Meanwhile, the optimum number of satisfiable clauses, c score j, can never exceed the same sum, underscore j equals 1 caret my asterisk underscore j. Dividing these two results, we get DROT. EC slash C times is greater than or equal to 1-to-1 slash E approximately equals 0.673. Meanwhile, and there you have it, our 0.673 approximation guarantee. Building on our approximation guarantee, let's visualize the linear program in 2 dimensions. On screen, the horizontal axis represents x, the vertical axis x, and the blue polygon marks the feasible region defined by constraints like a file x is less than or equal to b, shown in green. The red dot on the boundary is the exact LP optimum, x underscore optimal, and the tilted red line with an arrow shows the objective direction circa. Randomized rounding takes that fractional LP solution and gives it a gentle, random nudge to a neighboring integral point inside the blue region. In effect, it performs a local search around the LP optimum, exploring nearby corners and edges in hopes of landing on a high-quality integer solution. Now let's turn to our key findings on approximating maxset. First, we achieve a randomized 1-1e approximation, about 0.637, which clearly outperforms the baseline 0.5 guarantee. In both theory and experiments, our elder sibling algorithm consistently beats the classic 0.5 approximation younger sibling method. And since it's randomized, you'll want to run it multiple times to obtain reliable, stable results. Building on our previous insights, let's dive into two key observations about randomized rounding for satisfiability. First, in the younger sibling algorithm, each clause C_J is satisfied with probability. PR_C_J is satisfied, is greater than or equal to 1/2 J. Consequently, as long as every clause has size at least 2, this simple scheme already guarantees a 0.75 approximation. Second, the older sibling algorithm refines this bound by leveraging the LP solution Y*_J for each clause. Now, PR_J is satisfied, is greater than or equal to 1 C_J, **J. When every clause has size at most 2, this stronger estimate also yields a 0.75 approximation. In other words, by selecting the appropriate rounding strategy based on clause size, we achieve the same 0.75 approximation guarantee in both regimes. Building on those two rounding strategies, let's call our new method the full family union algorithm. It simply runs both the younger sibling and the older sibling approaches, and then picks whichever one yields the better solution. By merging and choosing between these two strategies, the full family union algorithm guarantees at least a 0.75 approximation of the optimum. To formalize our set cover problem, we introduce a binary variable x for each set S. X equals 1 if we pick that set, and 0 otherwise. Our objective is then to minimize the total number of chosen sets, written succinctly as minimize x. To guarantee every element is covered, we impose a constraint for each point in the universe. The sum of x over all sets S containing that point must be at least 1. In the example diagram, you can see 6 overlapping sets, S through S, each enclosing various points. Thanks to our coverage constraints, every teal point falls within at least one selected set. And by enforcing x element of 0, 1, we make sure each set is either in or out of the solution. No half measures here. Now, building on our previous discussion, let's formalize the integer programming model for set cover. We introduce a binary decision variable x that equals 1 if we pick the k-th set and 0 otherwise. For each element I, we define S as the collection of all sets containing that element. Our objective is to minimize the total number of chosen sets, written as minimize x. To ensure every element is covered, we add one constraint per element I. The sum of x over all sets in S must be at least 1. In other words, each element must appear in at least one selected set. In the diagram, the green circles represent elements, and the outlined regions labeled S through S are our candidate subsets. We choose a subset of these regions so that every circle lies inside at least one selected area. Finally, by enforcing x element of 0, 1, we guarantee that each set is either fully chosen or not chosen at all. That completes our integer programming formulation of the set cover problem. Continuing from our earlier formulation, we now model the set cover problem by introducing a binary decision variable x for each of the 6 candidate subsets S through S. Our objective is to minimize the total number of chosen subsets, written as the sum from k equals 1 to 6 of x. To guarantee that every element, the green circles, is covered, we impose a series of covering constraints. For example, x plus x is greater than or equal to 1. X plus x is greater than or equal to 1, and so on. In the illustration, each irregular shape corresponds to one subset covering specific circles, and the integer restriction x element of 0, 1 forces us to either pick or exclude each set. Building on our model, let's look at the original covering problem on the left. We minimize the sum of binary variables x, ensuring each set S contains at least one selected element. Next, by relaxing the integrality condition, replacing x element of 0, 1 with continuous y element of 0, 1, we arrive at the LP on the right, still enforcing each set's sum is greater than or equal to 1. In other words, we've lifted the integer restriction and now allow fractional choices. So how do we take this LP solution and recover a valid integer solution? That's exactly where our iterative LP relaxation algorithm comes into play. Building on that relaxation idea, we now take a two-step approach to tackle our covering problem. First, we formulate it as an integer program, minimize the total x, where each x is binary, subject to the covering requirement that for every set S, the sum of x over k element of S is at least 1. Next, we drop the integrality constraint, letting each x become a continuous y element of 0, 1. We keep the same objective and the same sum over each S is greater than or equal to 1 constraints, but the problem transforms into an LP that can be solved much more efficiently. Now, building on the LP relaxation we just introduced, we'll walk through an iterative LP relaxation algorithm in 3 clear steps. First, we cast our combinatorial problem as an integer program, minimize the sum of binary variables x, ensuring that each constraint set S has at least one member selected. Second, we relax the integrality requirement. Each variable y now ranges continuously between 0 and 1, yet we keep the same objective and covering constraints. Third, we solve this relaxed linear program to obtain an optimal fractional solution. For instance, y equals 0.2, y equals 0.7, y equals 0.5, and so on. Although the LP returns these fractional values, our ultimate goal remains recovering the original integer variables x element of 0, 1. By laying the two formulations side by side, it's easy to see how the binary constraint x element of 0, 1 is replaced by the linear bound y element of 0, 1, while the core objective and coverage requirements stay exactly the same. Building on our LP relaxation discussion from the last slide, let's walk through the full iterative algorithm in 3 steps. First, we cast our problem as an integer program, defining each binary variable x, the objective to minimize their sum, and the coverage constraints. Next, we relax the integrality requirement so each variable y can range freely between 0 and 1, turning our model into a linear program. Finally, after solving this LP to optimality, we apply randomized rounding. For each variable, we set x to 1 with probability equal to its LP value y. This approach marries the efficiency of LP solvers with a straightforward rounding rule to yield a feasible integer solution. Building on our previous discussion, let's walk through our 3-step LP relaxation algorithm. First, we cast the covering problem as an integer program. We minimize the sum of binary variables x, ensuring that for each set S, the total of its x's is at least 1. Next, we relax the integrality requirement and let each variable y range freely between 0 and 1, producing a linear program with the same objective and covering constraints. Finally, after solving this LP to optimality, we perform randomized rounding to recover an integer solution. For each index k, we independently set x to 1 with probability y. For instance, if y equals 0.3 and y equals 0.7, a typical outcome might be x equals 0 and x equals 1. This approach combines efficient LP solving with a simple, probabilistic rounding step to yield a feasible covering solution. Continuing from our LP relaxation rounding, this slide highlights a violation of the very first criterion, feasibility. In other words, our proposed solution isn't practical in its current form. It may fail to deliver real-world results or simply can't be implemented given our constraints. The challenge before us is clear. What modifications or alternative approaches can we adopt to restore feasibility and turn this idea into a workable solution? As a remedy to our feasibility challenge, let's explore a Monte Carlo approach for integer programming. We begin by formulating the problem as an integer program, then relax the integrality constraints so we can efficiently solve it as a linear program. Once we've obtained the LP's optimal fractional solution, we apply randomized rounding to generate an integer candidate. Because rounding can sometimes violate constraints, we iterate, reformulating the IP, relaxing it, and rerunning randomized rounding until every inequality is satisfied. In the end, each variable is set to 1 if it was ever rounded up in any iteration, and 0 otherwise. Building on that framework, let's walk through the iterative loop for solving integer linear programs by successive relaxations. We begin with our original ILP and simply drop the integrality requirements to form a relaxed linear program. That LP feeds into a solver, which returns a fractional solution. Next, we round or extract that solution into a candidate integer assignment and check it against every original inequality. If we spot any violations, we add the corresponding constraints back into the relaxation and resolve. Whenever our candidate passes all the checks, we accept it as the final integral solution and exit the loop. In short, we relax, solve, round, check, and refine over and over until no constraints are violated. Building on our iterative refinement, this slide shows how to form a feasible solution by taking the union of all sets chosen across iterations. In formula form, we simply set each variable x to 1 if it ever appears in any iteration, and to 0 otherwise. The table on the bottom illustrates this with 5 variables over 3 iterations. X is chosen in iterations 1 and 3, so its final value is 1. X appears in iterations 2 and 3, so it too ends up as 1. X and X are never selected, so they stay at 0. X is picked only in iteration 1, giving it a final value of 1. With this union rule, any variable selected even once remains in the solution, guaranteeing feasibility across all iterations. Now let's turn to the classic set covering formulation. Here, each decision variable x is 1 if we select set k, and 0 otherwise. Our goal is to minimize the total number of sets chosen, that is, to minimize the sum of all x. Each constraint corresponds to one of the blue points and ensures it's covered by at least one selected set. For example, the top left point appears only in sets 1 and 3, giving us the constraint x plus x is greater than or equal to 1. The other points generate similar at least 1 inequalities. On the right, you can see the diagram of the 6 candidate sets S through S and how they overlap the 9 points. By enforcing these constraints and keeping x binary, we end up with the smallest collection of sets that covers every point. Building on that classic set cover formulation, this slide illustrates the core loop of an iterative relaxation scheme for integer linear programs. We begin with a fully integral candidate solution and first check whether it satisfies every inequality. If it does, we're done. Mission accomplished. We have our integer solution. If it fails any constraint, we drop the integrality requirement and hand the problem off to a standard LP solver. That solver returns a fractional solution, which we then convert back into a new integral candidate, often by simple rounding, or another combinatorial trick, and feed it back into the feasibility check. This cycle, check constraints right pointing arrow, solve relaxed LP right pointing arrow, generate integral candidate, repeats until every constraint is met. In our analysis, we focus on 2 key questions. How many iterations might this require in the worst case? And how close will the final integer solution be to the true optimum? Building on our previous discussion, this slide walks through the core loop we use to turn an integer linear program into a valid integer solution by iteratively solving its relaxation and checking for violated constraints. We start with the original integer program, relax it into a standard linear program, and hand it off to an LP solver. The solver returns a fractional solution, which we then convert, often by rounding, into an integral candidate. Next, we test whether this candidate satisfies all of the original inequalities. If any constraints are violated, we feed that information back into the linear program, add new cuts or make adjustments, and resolve. Once every constraint checks out, we update our integer model and repeat the cycle. The 2 key questions we're raising here are, how many iterations will this loop take on average? And what's the chance we'll have to run it again at all? Building on our iterative cutting plane loop, we now model the set cover problem as a 0 to 1 integer program. On the right, you'll see 12 points arranged in a grid and 6 overlapping regions labeled S through S. Each region is a candidate set that covers the points inside it. We introduce a binary variable x for each set S, and our goal is to pick the fewest sets possible. Formally, we minimize the sum of all x, subject to one covering constraint per element. For example, the highlighted constraint, x plus x is greater than or equal to 1, ensures that this particular element lies in at least one chosen set. Whenever any such constraint is violated, we add it to our model and resolve. We repeat this process, add a violated cut, resolve, until every element is covered and all constraints are satisfied. At that point, our solution gives an optimal set cover. Now, building on our integer program model, we dive into the heart of the randomized rounding analysis. When we randomly round each fractional variable y, the probability that a specific constraint with r terms fails is simply the product over k equals 1 to r of 1y. To make this concrete, on the left we have the original 0 to 1 integer program with 6 binary variables, x through x. Our goal remains to cover every constraint. Think x plus x is greater than or equal to 1, x plus x is greater than or equal to 1, x plus x is greater than or equal to 1, and especially the highlighted x plus x plus x is greater than or equal to 1, while minimizing the total number of chosen sets. On the right, you see the LP relaxation. Each x becomes a fractional y in 0. 1. We enforce that the sum of y's in each constraint is at least 1, and we minimize an airy summation y. These fractional values then dictate our rounding probabilities and feed directly into that product formula for the failure probability of any single constraint. Building on our last result, let's now quantify the chance that a single covering constraint remains unsatisfied when we move from the fractional LP solution y to a random integer choice. On the left, we express the failure probability exactly as the product over k of 1y. Then, by invoking the AMGM inequality, we bound this by 1yr arts. Since our LP guarantees y is greater than or equal to 1 for any constraint of size r, we get a further bound of 1 to 1 r. In plain terms, each constraint is left uncovered with probability no greater than 1 to 1 r, which tends to 1e as r grows. Finally, at the bottom we restate the contrast between the original integer program, minimize x with x element of 0, 1, and its LP relaxation, minimize y with y element of 0, 1. That relaxation underpins our rounding analysis and leads directly to this elegant probabilistic bound. Building on our previous probabilistic framework, let's now bound the chance that a single covering constraint remains unsatisfied after r independent rounding steps. We begin with the exact failure probability. Underscore k equals 1 caret r, 1y. And by the AMGM inequality, obtain 1y is less than or equal to 1yr. Since our LP relaxation guarantees y is greater than or equal to 1 for each constraint, this gives 1 to 1 is less than e caret minus 1. In fact, if the total fractional weight is lambda instead of 1, then as r grows, 1 lambda slash r right pointing arrow e caret lambda. So the failure probability decays exponentially in lambda. Below this derivation, we contrast the two formulations of our covering problem. On the left is the original integer program, minimize x, subject to each set constraint, underscore k element of s. X is greater than or equal to 1, with x element of 0, 1. On the right is its LP relaxation, minimize y under the same covering constraints but allowing y element of 0, 1. This relaxed program is what we round iteratively, and the bound above shows each constraint fails with probability at most e caret minus 1. Building on that bound, we now see how the probability of satisfying our constraints grows as we run more rounds of randomized rounding. After t iterations, any single constraint is met with probability 1-1/e caret t. Because we need all k constraints to hold simultaneously, the overall success probability becomes 1-1e caret t e caret k. Below these formulas is a small table illustrating 3 constraints over successive rounds. Constraint 1 is satisfied in iterations 1, 3, and every round thereafter. Constraint 2 first fires in iteration 2 and remains satisfied. Constraint 3 never fires. To form our final solution, we take each decision variable x and set it to 1 if it was ever rounded to 1 in any iteration. Otherwise, we leave it at 0. Now let's bound the probability that after t iterations, all k constraints remain satisfied. We start with the exact expression. 1 lash e caret t caret k. Next, By invoking the standard limit, 1 to 1 / r caret r, right-pointing arrow e, we can approximate this probability as express k by e caret t. Here's the key insight. If we set t equals ln k, then e caret t equals k, so the exponent becomes net of k per k equals -1. In other words, after about ln k iterations, our algorithm succeeds with probability roughly e. Building on that result, we now ask two key questions. How many iterations are required, and how good will our final solution be? We'll show that the cutting plane method converges in O log k iterations. As the flowchart illustrates, we start with our integer linear program and relax it to a standard LP. An LP solver then produces a fractional solution from which we derive an integral candidate and check it against all original constraints. If every inequality holds, we've found a valid integer solution. If not, we identify the violated constraints, add them as new cuts, and resolve the LP. Each cycle tightens the relaxation until we recover the exact integer optimum. Building on our cutting plane discussion, let's now compare the original integer program with its linear relaxation. On the left-hand side, we have an IP that minimizes the sum of binary variables x, subject to the rule that for each demand pair, p, p, at least one selected cut x must equal 1. On the right-hand side, we relax each x into a fractional variable y in 0, 1, while keeping the same coverage constraints. We call the optimal value of this relaxed LP opt LP. Because every integer solution is also a feasible LP solution, it follows that opt LP is less than or equal to opt IP. In other words, the LP optimum gives us a readily computable lower bound on the true integer optimum objective. Building on that LP lower bound, let's denote ZZZ as the objective values of the integer subproblem we solve in each iteration. First, we show that the expected value of any single z matches the sum of the corresponding fractional variables y, and so it can never exceed opt LP. In formula form, equals y is less than or equal to opt LP. Next, to bound the expected size of our final cover C, we simply add up these expectations over all t rounds. Equals e is less than or equal to e underscore p equals 1. Caret t z is less than or equal to t quachake ylp. Finally, by choosing the number of rounds t equals OLNK, we drive the expected cover size down to OLNK op top LP, and since OPLP is less than or equal to op AP, this gives us an O log K approximation guarantee for the algorithm. Building on that result, our algorithm has two standout features. First, it runs in just O log K iterations, where K is the number of elements. Second, its LP relaxation framework ensures an O log K approximation in solution quality. In other words, both the running time and the approximation guarantee scale only logarithmically with the problem size. Now that we've seen those logarithmic guarantees, let's dive into why LP relaxation is such a powerful approach for nitrogen monophosphide hard problems. You start by solving a relaxed linear version, then use its fractional solution to guide your search for an integral answer. In practice, LP relaxation shines when that fractional solution reveals meaningful insights into the original problem structure. The critical step is the rounding algorithm, which converts those fractional values into a valid integral solution. With a strong rounding strategy in place, LP relaxation becomes an effective tool for approximating even the toughest combinatorial challenges.